Welcome to the last video in SLO10. In this video, we'll be looking at reactions in which we react alpha-beta unsaturated ketones that look like this with carbonyl species that could be either cyclic, in this case for the example we'll do, or acyclic, under these kinds of conditions, which probably remind you a little bit of some reactions you might have seen in SLO9, specifically Aldol condensations. So to get started thinking about what we might form, we have to assign roles like we always do. And if I do that, there's a bunch of possibilities. So I see that I've got an electrophilic site. Let me actually do this in blue. An electrophilic site here. I've got an electrophilic site. So both of the carbonyl carbons, right? We also learned earlier on in this SLO that the beta carbon, because of its conjugation to a carbonyl or other electron withdrawing group, that we have three different electrophilic sites. Let's also find our nucleophilic sites. So we've got both ends of our ketone. This is a symmetrical ketone, so I'm just going to label the one carbon. But I also have this carbon here, which could become nucleophilic because there is a base. Okay, so one thing I do want to point out here is that in these alpha-beta unsaturated carbonyls, to start, this alpha carbon here is not actually nucleophilic, right? The proton on this carbon, because of the alkene being there too, is actually not very acidic for reasons that I'm not going to get into now. If you're really curious about it, you can email me and ask, or we can talk about it in office hours. But initially, the only place I can reasonably deprotonate on this alpha-beta unsaturated ketone is the methyl group here, right? So the carbon that's sp3 hybridized. So that means I've got a lot of possible reactions. I could, use this nucleophilic site to react here. I could use this nucleophilic site to react here or here. How do I know what's going to happen? And probably you're looking at this and saying, like, I don't know, like, aren't you just going to get a mess? Like tons of different products. Why would I ever do this? Awesome question. But it turns out that this reaction is actually pretty highly selective. And what ends up forming is an interesting looking product. So we end up making a compound that still has a 6-membered ring, shocker, right? That's our cyclohexane, as well as the 4 carbons here. And it turns out that we're going to form 2 new carbon-carbon bond frameworks. So we'll form a new carbon-carbon bond here. We'll end up forming a double bond here, so carbon-carbon double bond. And then finally, we have a carbonyl here. So that's pretty highly colored, right? Lots of different things to notice. The red is going to be the new bonds that form in this reaction. Green, this is showing you where the carbons are coming from, which are the 2 starting materials. So I'm also going to redraw this all in black so that it's a little bit easier to see what the overall product looks like. So that would be the same structure, but rendered just with one color. So this is a really kind of an interesting reaction. And what I want to do in this video is actually go through the mechanism for how we form this compound, because it'll highlight a bunch of the themes that we've seen in SLO9 and 10. It's a great way of essentially encapsulating a lot of what we've done over the last couple of weeks. So the last thing that I want to do is introduce this reaction. It has a name. It's called the Beyonce reaction. Because, well, I bet you can figure out why we call it this. So let's get started with the mechanism. So if we look at the bonds that we're forming here, there's a couple of things that we can do. We can actually trace where those new carbon-carbon bonds are relative to, and let's focus on our green piece, on our alpha-beta unsaturated ketone. So it looks like this new double bond is from this methyl group, right, adjacent to the carbonyl. So I'm going to start putting in some letters. I'm going to erase all my N's and E's. So I'm going to call this carbon A, B, C, and D. And then I'll just put the same numbers on my starting material. So A, B, good check is that B is a carbonyl in the starting material, and it's also a carbonyl in the product. And then C and D. Okay, and then I'm going to actually use numbers for the parts of my other reactant that change. So here we'll just do 1 and 2. So I need to figure out where carbon 1 is and where carbon 2 is, and I can do that by thinking about now the role of carbon D. I'm going to focus on the bond between D and 2. So that bond formed by D being an electrophile. This is the beta carbon of an alpha-beta unsaturated carbonyl. And that means that carbon 2 needed to be nucleophilic, right? So I've now decided that this carbon is electrophilic, this carbon must have been nucleophilic, and if I look at what I'm starting with, where that carbon comes from, I need to find a place that could be nucleophilic. Well, under the conditions, this alpha position here is going to be nucleophilic. So it's likely that the 2D bond comes from an enolate at carbon 2 reacting with our beta carbon, or in other words, a Michael addition. And so if this is 2, I now need to think about how I'm making the 1A bond. So I know that A in my alpha-beta unsaturated ketone is a methyl group adjacent to a carbonyl. A could be nucleophilic because of the presence of base. I know that I'm refluxing, so this sounds like an aldol condensation. And that's going to give rise to a CC double bond. So it sounds to me like carbon 1 is this carbonyl carbon in my starting cyclohexane, or cyclohexanone, excuse me. So you can see how important it was to essentially toggle back and forth between our lettering and numbering systems and roles, electrophiles and nucleophiles, to kind of get a sense for what kinds of bond-forming events are occurring here. Otherwise, these problems are really too difficult to solve, right? We need to create a template or a framework for ourselves to get started. So it turns out that the thing that we know now after kind of a lot of experimentation on the mechanism is that the first bond that forms is this bond here between what I've labeled 2 and D. So this is my first CC bond that forms in mechanism. We know this because we actually were able to isolate some intermediates along the way in the reaction, and we see that they usually involve this bond, but not the 1 to A bond. So we need to think about forming that 2D bond. So we'll start with our 2 reactants. I'm actually going to drop the coloring now. It's just going to take me too long to keep switching back and forth between pens all the time. And so what we've established is that carbon D here is our electrophilic site, and we've established carbon 2 is our nucleophilic site, but right now carbon 2 is not nucleophilic. So the first thing I'm going to do is actually make it nucleophilic by deprotonating it with our base, which is ethoxide. I'm going to drop the sodium, it's just a spectator here. So the first thing I'm doing is enolate formation. I like to draw my enolates in their major resonance structure form, so you're welcome to draw them as carbanions if you like. And we know that this acid-base reaction actually should be kind of unfavorable, right, because we're going to be making ethanol, a stronger acid, from our ketone, which has a pK of about 20. But I will get some enolate, just a little bit. And this enolate is now primed to act as a nucleophile toward our beta carbon. So as we talked about in the second video for this SLO, typically for enolates we're going to actually see selectivity for conjugate or 1,4 addition, right? And that's kind of why Michael additions have this name. And so we could reasonably predict that this would be the major pathway for this enolate to interact with this alpha-beta unsaturated carbonyl. So there is our conjugate or a 1,4 or Michael addition. I'm actually going to turn here. So this is our Michael addition, and that's going to give me a product that actually has this new CC bond in it. So I will highlight that bond in red. So that's my 2D bond. And the other thing that I know is that I have an enolate. Whenever we do these 1,4 additions, we always end up with enolate intermediates. So this is what I have after the Michael addition. And if I look at what I'm doing, it would be tempting to say, oh, okay, well, I've got an enolate, and I know that eventually that this carbonyl carbon is going to be electrophilic, where we decided that we've got that kind of reactivity going on here. So maybe I can connect this carbon to this carbonyl. So do something like this, and kind of the beginning of an intramolecular aldol. So let's see what I get if I actually do that. I'm going to show this going down. So I'm going to make a 1, 2, 3, 4, membered ring. So I think that would end up with something that looks like that. How likely is that? We talked about this back in SL09. These reactions are reversible, and so it's possible that this tetrahedral intermediate that I'm forming can collapse by regenerating the enolate, and that happens, right? And so we're basically trying to avoid all this ring strain, and so this equilibrium lies pretty far toward this open chain form where I have this enolate. So I'm at an impasse, right? I have an enolate, but it's not the right enolate. I can't do the Aldol condensation I'm spotting for this CC double bond because I need an enolate not here, I need it here. So the way that we actually rationalize how this occurs is that we're using a protic solvent. So this intermediate could be protonated. The enolate could be protonated. So we'll actually also add, I'm going to clean up my arrows here. Another possibility would be that a molecule of ethanol would get involved. This is a testable hypothesis, right? You could run this reaction in an aprotic solvent and see what happens. And in fact, you get stuck at this enolate. So it really does seem like the solvent effect is real. So we'll do an acid-base reaction where we protonate our enolate at carbon. And this particular acid-base reaction is actually favorable because I'm going to be making a weaker acid from ethanol now. So this is our new proton. This one's already been there, so this is the methyl group. And it looks to me like I'll also have ethoxide. Okay, so we know the final product. We know that this is the structure. We know we need to make carbon A nucleophilic. And here is carbon A, the CH3 group, right? Carbon A. So I need to make an enolate. Oh, but I have a base. Yes. So we're basically equilibrating between two enolates here. Either the enolate that runs into the side here, that's this compound, or the enolate that runs to the outside. That's the compound that we're generating now. So this part is also reversible. We'll make a molecule of ethanol. All right, and so now we're set up to make the first of the two bonds that we're calling the A1 connection. So that'll form a ring. A 1, 2, 3, 4, 5, 6 membered ring, which is what we observed. Okay, so that's going to put a ring on it. And we've got an O-, carbonyl, right? So this oxygen here is this oxygen. And that looks good. Okay. So we're not quite done. We formed one of our new CC bonds. I'll make that red. But we need to form another CC bond, right? We need to form a CC pi bond here, which means we need to lose this oxygen. So this is where we go from an aldol reaction. This was an intramolecular aldol. To an aldol condensation. And this is going to occur in a couple of steps, which unfortunately I may not be able to fit on the board. So the next thing that happens is, hey, wait, ethanol. We're going to keep protonating and deprotonating and protonating and deprotonating things. Turns out the choice of the solvent and the base is really important here. We need all these acid-base reactions to be reversible. So we'll first protonate this O-. That's essentially thermoneutral, right? We're trading one O- for another O-, right? But it is reversible. KEQ will be, somewhere close to 1. And so now we have an alcohol, tertiary alcohol. And we have ethoxide, the conjugate base of ethanol. So what do we have left to do? Well, we are going to need to form this new CC double bond, which is formally some kind of an elimination. I'm going to remove a proton, one of the two H's from this carbon here. So I'll draw one of them in. And I have to lose this alcohol. So I'm losing water overall. Right, that's what we mean by condensation in this case. And the way that this happens is by first deprotonating to make an enolate. That essentially builds up negative charge on the intermediate, which will overcome this problem with using OHs as leaving groups. Or typically, we don't think about those charges as stable enough, but if we already have O- in our starting material and we end up with O- in the product, we've kind of shrunk the difference, and that makes the leaving a little bit easier. So we will have another enolate. Should just rename this reaction "Fun with Enolates." And now we are going to flip it on the board. It's a miracle. Our elimination event. So we'll end up with hydroxide at the end. I noticed that the structures are getting a little smaller. Hopefully they're still legible. Okay, so a couple of things to point out here now that we've gone through this whole mechanism. None of this is new. Absolutely no step in here is new. We've talked about literally every single step in this mechanism in the last two SLOs. We've got enolate formation, which I'm sure you're sick of hearing about at this point. We've got our Michael addition or R14 addition, right? So that's what we're learning about in this SLO. We've got enolate protonation. We've seen this in both SLOs. Enolate formation, SLO9, right? Aldol, intramolecular aldol, SLO9. We saw that, and then aldol condensation, which is these two steps combined, forming an enolate and then injecting OH- as a leaving group. That's the aldol condensation, and we saw that in SLO9 also. So a lot of material that all goes together to do a pretty amazing structural change. We're making 3 new carbon-carbon bonds, and we're taking 2 compounds and making a ring, or in this case, we're adding a ring. We start with 1 ring, and we put a ring on it. So it's true that I like to call this reaction the Beyonce reaction, but it does have a name. It's named after the chemist that discovered it. This is also called the Robinson annulation. So this word annulation is essentially what the title of Beyonce's famous song should be. This is the idea that we're putting a ring onto something. Okay, so we've gone through the mechanism of this Robinson annulation. In the next section of this video, we'll just look at one example where we don't go through the mechanism and work on a stochastic way to predict products given the structures of the starting materials. So we're ready to look at some more examples of Robinson annulations. And in this section of the video, we're going to be focusing more on predicting the structures of products using a set of observations about structural change than working through the mechanism again. I want to be clear that it's important that you can both use some of the kind of shortcuts that we're going to develop in this video or this section of the video. But it's also important that you can work through the mechanism of a Robinson annulation fairly quickly and without too much trouble. It's never sufficient to only know the shortcuts. And really, if you ever get stuck, if the shortcut seems to be not working or there's some wrinkle you're not sure about, that's when you use the mechanism, right? So it's really important that you know why the shortcut works. If you don't, then you don't really understand the material. So what we're going to do is first focus on the fact that the Robinson annulation proceeds in a predictable fashion with respect to the order of events. So the first step is always going to be, or the set of steps, it's going to be the Michael addition, right? So we're going to form a CC bond between the beta carbon of an alpha beta unsaturated carbonyl and the alpha carbon of a ketone or an aldehyde, so that would be like an enolate, for instance. So this tells us what electrophilic site we have, right? The beta carbon of alpha beta unsaturated carbonyl That's the electrophilic site. And it also tells us that the alpha beta unsaturated ketone is the electrophile, and that means the other reactant must be the nucleophile. Okay, so what that means for the specific reaction that we'll look at is that this compound must be the electrophile, and that the beta carbon here, that's going to be my electrophilic site. So that's simplifying because now I'm just dealing with one electrophilic site out of the possible three that exist between these two compounds. And because I know this structure is the electrophile, then I know the other carbonyl-containing species, that must be the nucleophile. So now what's all left for me to do is figure out which site within this molecule is the nucleophilic site. And in this case, I've got two alpha positions that are equal to each other, so I'll just choose one arbitrarily. So I'll choose the one on the right. So that position would be nucleophilic. I see that I have a base that will reversibly generate an enolate, so a lot like ethoxide here. So I know that I can have nucleophilicity here. So that helps me get started. I know kind of what kinds of connections I'm going to make. I'm going to end up forming a CC bond from this carbon to this carbon. And then I know that the second part of my Robinson annulation process is an intramolecular aldol. Condensation, because I'm refluxing. And this also tells me something, right? It tells me that the carbonyl carbon of what was my nucleophile is now going to be my electrophile. So carbonyl Michael nuke becomes electrophilic, or becomes, it's always electrophilic, but becomes the electrophile. And we also know that it's going to be the other alpha position of the alpha beta unsaturated ketone that will become nucleophilic. So that means that if this is my Michael bond that I'm forming, then my aldol condensation will be that. So having a general sense for how we're going to do this is kind of helpful. The third observation, which isn't necessarily like an order of addition or order of reactions that are happening, is that we'll end up essentially transposing a double bond. We'll see that in just a minute. So I could work through this and draw some structures and adjust and erase, and that's fine. One of the things that I note here, so notes, is that I'm always going to end up making a six-membered ring from this Robinson annulation. There may be other rings also in the product, but they'll come from one of the reactants. And those rings can be whatever size, right? But we're going to make a six-membered ring. All right, so we're making a six-membered ring. We now know what kinds of bonds are going into it. So what we can say is that it looks to me like we're using 2 carbons from the nucleophile and 4 carbons from the electrophile, and those are all going to end up in this new six-membered ring. Right, so 4 carbons from the alpha beta unsaturated carbonyl reactant and 2 carbons from the other thing, which we'll call, I guess, the nucleophile. Okay, so that means that we're always going to end up with 4 carbons from our alpha beta unsaturated system and 2, so like that. So I've basically templated them into what's going to look like a six-membered ring. And I know that we'll form new bonds. So here and here. And so I can start transposing all the groups onto this template that I'm starting to build. So I know that of these two carbons, right, that we've got a carbonyl and a ketone. So I'm going to go ahead and number those. So we'll call the methyl group 1, ketone carbon 2, other methyl group 3. So 1 is connecting to the beta carbon here. I'm also going to put some letters on this guy. So A, B, C, D, and E. So I'm making a 1 to B bond. So we'll note that of these 4 carbons that are involved, the alpha beta, or the beta carbon of this unit is always going to be connecting. It's a point of connection here. So we'll say this is B, and that means this is C, this one's D, and this one's E. And we can also add our numbering from our nucleophile. So this would have to be 1, this would have to be 2, and then it looks like 3 is missing. So we can add that now. We know that 3 is attached to 2. Okay, so just to check this, I should have made a bond between 1 and B. 1 and B. That was my Michael addition. Cool. That makes sense. B would be beta to carbon B, which is the carbonyl, so I can add that. All right. And then I know that I'm going from E to 2, I'm making a bond, but I'm doing it in an intramolecular Aldol condensation, so there should be a double bond. Okay, so it looks to me like I've done almost everything. I'm just missing one group now. Whatever is attached to carbon E, for instance, or C, I need to add those substituents. So E has a phenyl group. Okay. And that's it. I've added everything now. So if I actually went and drew this as a product with like real bonds and stuff, it would look like that. So you can work this with this kind of pattern recognition where you know you're making a 6-membered ring. You know where those bonds are, 4 atoms from the alpha beta unsaturated unit, 2 from the other reactant, right? And you can kind of template yourself like this and fill in your substituents, right? So let's look at another example here. I'll clean up my board. All right, and so let's do a structure that looks like this, and then let's choose another alpha beta unsaturated ketone. So we'll use this one. Okay, and remember I can use pretty much whatever kind of alkoxide or hydroxide base and solvent base I want to use. So let's use MEOK, so potassium methoxide, methanol, and reflux. That works too. So, you know, the combination of an alpha beta unsaturated carbonyl like this, these kinds of ketones, and solvent and base combinations with reflux like that, I'm starting to think about Robinson annulations here. And so I'm going to play the same game. For me, I always orient my structures the same way, where the carbonyl of the alpha beta unsaturated unit I'm going to put pointing straight up. I'm going to orient those 4 carbons that were a part of the alpha beta unsaturated system itself, so that doesn't include the methyl yet, right? Just those 4 carbons are here. And then I'll take this structure and put my 2 carbon piece on. And then what I'm going to do next is figure out, well, whoops, what kind of substituents need to go where. So that would be my Michael addition CC bond. Here is my carbon-carbon double bond that's forming from the Aldol condensation. And I'm just going to number and letter. So this will be A, B, C, and D. A, B, C, and D. So I'm going to check this. C should have a carbonyl in both structures. It does. Carbon A should be the beta carbon from the carbonyl. In this structure, it definitely is. It is here too. So alpha, beta. That looks good. And then I'm going to put my numbers in. So I know that the other part of the CC double bond that's forming here from the Aldol condensation needs to be the carbonyl from my reactant that's not the alpha beta unsaturated system. So I'll call this carbon 2 because I'm going to have to choose a 1. I don't want to like skip numbers or invert them or something like that. So here's carbon 2. But in this problem I need to be careful because now I have 2 different nucleophilic sites. These are no longer equivalent like in the previous problem, so I actually need to decide which of them will form. So which enolate will form. And I think it would actually be good for you to decide this, right? So pause your video and decide which of the 2 enolates I could make, I will make under these reaction conditions. Right, so you've had a chance to work through this, and what you might notice is that really the base is going to tell us what we need to know. Methoxide is not a strong enough base to irreversibly form an enolate from a ketone. The protons on either of my 2 potential alpha positions have pKa's around 20, whereas methoxide would make methanol from this reaction with a pKa of 15. So I'm making small amounts of enolate, and that tells me I'm going to make the most stable enolate. So we've got a reversible enolate formation. Spelling mistake number 1 for the video, awesome. Reversible enolate formation, which tells us more stable enolate, which tells us more substituted enolate. Okay, so if I look at my 2 possibilities, I've got an enolate that would run out this way, which would have just 1 substituent, or I could form an enolate here, which would have 1, 2 substituents. So this would be the nucleophilic site for me. And now I can add my numbers. So if this was 2, I'm going to have to make this 1, 3, 4, 5. So it looks good. So here's why this is important. I could have put 1 or 3 here, but I know that if this is my nucleophilic site, this is the carbon that ends up bonded to the beta position. Right? So remember that the bond I would be making here would be from 3 to A. That would be my Michael. So that means that this carbon is 3. I'm actually going to move that number just a little bit. So 3, and then I know that I've got carbon 1, which is apparently not a part of the new ring. It's going to be sticking off of it. So I've got a methyl group that sticks out like this. That's carbon 1. And then carbon 3 is going to have carbon 4 and carbon 5 attached. 4 and 5. All right, and so then the last thing I need to do is add in substituents on my alpha beta unsaturated unit. So at carbon B, I've got a methyl group, and that will be true here as well. Okay, so if I now take this out of my template to draw a structure with no dotted bonds or whatever, looks like that's what I will end up with. So we've looked at a couple of examples of the Robinson annulation. There's practice in the SLO document, both with respect to the kind of the pattern recognition as well as thinking critically about the mechanism. There are actually lots of different kinds of structures you would identify as potential nucleophiles or as potential partners using the aldol or the alpha beta unsaturated carbonyl species that don't work in the Robinson annulation. And the reason why is that there's some structural feature in one or more of the reactants that doesn't allow one of the steps to happen. Like maybe you can't do the Michael addition, or maybe you couldn't, once you've done the Michael addition, maybe you couldn't do an enol or an aldol condensation. Like those are possibilities. And they're sometimes hard to spot if you're just looking at the structures themselves. That's why it's so important to have a facility with working through the mechanism and understanding its consequences. So this is going to conclude our coverage for SLO10. We've looked at the electrophilicity of the beta carbon. We've looked at a bunch of different kinds of nucleophiles that will actually react with the beta carbon, and talked a little bit about how you might predict selectivity. We've talked about cuprates, and we've also talked about Michael additions and essentially the ultimate expression of all of this enolate chemistry and beta carbon electrophilicity, the Beyonce reaction.